Good morning and welcome to today's video where I'm going to discuss with you what are called transformations of functions. In this video we are going to examine how to take a particular function and basically change its appearance, and we're going to look at three different types of transformations we can make with a function, and those three transformations are referred to as translations, stretches, and reflections. So we're going to kind of focus in on today's video just the translations part of it. So I'm going to take what you already would have acquired for knowledge in regards to quadratics from last year, and I'm just going to show you that in some ways you were actually doing transformations without maybe realizing you were doing transformations or us calling them specifically transformations. So if I look at this function, quadratic, based on what you learned last year, you can tell me some things about its appearance. You can tell me that it opens down. Well, little do you know, that's a transformation. That's called a reflection. We have a stretch factor. I'll just put SF of positive 2. That's because of this 2 here. The reason it opened down was because of this negative here. We also know that this graph has a vertex of -3, -1, which tells me that what we refer to as the base parabola, y equals x squared, would get moved left 3 and down 1. So this would be an example of what we call translations. This here obviously is what we call a stretch factor, because we still called it that last year. This would be an example of a reflection. So those are just kind of fancier names maybe we didn't use last year, but you were actually doing that last year and identifying those. What we're going to do is apply that now to any function. It doesn't have to just be a quadratic. It can be any type of function, and we can deal with transformations. And as I said in this video, specifically translations. So let's identify what a translation is. So to translate a graph is to take a graph without changing the shape of it in any way and either move it left, right, or up, down. That's called a translation. They can be summarized with function notation as you see in this little chart down below. So I'll just kind of talk about these. Assuming that c is a positive number here, it's saying that if you just take some function, f of x, and you put a plus c, meaning plus some number at the end of it, it will take that graph and move it c units up. Now, this is, as I said, it's generic. Our experience last year was with y equals x squared. So imagine if I just replaced f of x with x squared, and I said, well, if I had y equals x squared plus 2, because of the plus 2, it's going to move it up 2. Well, what I want you to realize is that it doesn't matter. Yes, it worked in quadratics, but it also works in square root graphs. That would move up 2. It works in cubic graphs. That would take x cubed and move it up 2. It can be specific to any type of function, but putting numbers in the same location will have the same effect in terms of transformations. Looking at the next one says, well, take your function and put subtract c at the end of it. Well, that's going to move your function down c units. Much like here, if this was a -3, it would move down 3. Now, this one, to take your function and move it left or right, you have to insert your number inside the function. I said, I don't understand. What does that mean? Think of it this way. If you had f of x equals x squared versus g of x, which was this function, x plus 3 squared. Think of your knowledge of quadratics. This would tell me that by having the x plus 3 in here, which means I've put it inside where the x used to be, so x minus c means it's going to get substituted in where the x used to be, like so. This, I know, goes left 3 from my quadratic work. Well, what I'm telling you is that I don't care whether it's that or it could be the square root of x. If I then said g of x is the square root of x minus 7, I know that this graph is going to be 7 units to the right of this base graph because I put the minus 7 in here. If I then decided to put a plus 3 out at the end, this graph's going to go right 7 and also up 3. It would have a horizontal translation and a vertical translation. Now, here's a nice visual to show you translations. The middle graph right here is your base function. So if I took a base function and I add some number out at the end of it, it's going to move it up whatever c units is. If I took that function and I put a minus c inside the function, it's going to move my graph right c. If I put a plus c, it's going to move my graph left c. And if I put a minus c outside the function, it's going to move my graph down c units. All right, so that's a nice visual to show you horizontal and vertical translations and demonstrate where you'd have to substitute numbers to shift functions in those directions. So having seen that, if I look at some specific examples, if I looked at this function, you should be able to identify to me what type of translation that we're dealing with. This would be a horizontal translation of left 7 because it's been inserted in place of where the base, so your base function here would have been x squared. Well, x has been replaced with x plus 7. That has an effect of moving the opposite direction of that sign. So this would go left 7. Looking at this one, my base function would be the square root of x. I want to move my graph, in this case, up 3. So my translation is a vertical translation of up 3. Couple more here that I'm looking at. All right, looking at this one, so I can see that the base function, f of x, must have just been the square root of x. Well, I've inserted a minus 3 in where the x used to be, so that should move my graph right 3. Remember, that one's the opposite. And then this outside should move my graph down 2. So this one had both a horizontal and a vertical translation. Now this one is a bit more obscure function that we haven't worked with much, but it's called the reciprocal function. 1 over x would be the base. I can see that I have a minus 5 here, which would make it go right 5. And I have a plus 7 out here at the end, which would move my graph up 7. Now if I look at reading it from table of values or tables of values, I want to show you something called mapping notation. This will become a very important element in this course that we will use a little bit in this unit where we show you how it works, but it does become a really big part of 2 other units that we do in the course. So it's going to be really, really important that you get your brain wrapped around the whole idea of how a mapping notation works and what it means and how to create them. Well, if I examine a base function, so this is y equals x squared, and I look at the x values and the y values, and then I said to you, I want to look at x squared plus 2. So without looking at these tables, you should be able to tell me that's going to move my graph physically up 2 units. Well, I want you to think about taking a graph and moving it up 2 units. If you move a graph straight up in the air, the x value shouldn't change. It's going to go vertically above where it was or below, whichever direction you go, but your y value should change. So notice in this situation, the x value stays negative 3, but my y value gets adjusted and becomes 11 because it went up 2. This y value went up 2. This y value went up 2, and so on and so forth. In this situation, because I put the x minus 5 in there, that should move my graph left 5. So if we think about that, if you take a graph and physically slide it to the left 5, well, if you go straight across, the y value should not change, but your x value should change. So if you look at this one, the y value is 9. Well, the y value is 9 normally in the beginning when x was negative 3. But because we're shifting it to the left 5, not left 5. It's a minus. It's always the opposite. This should have been right 5. Good thing I looked at my data more carefully. So I should have been saying right 5 here. So if I'm going right 5, so negative 3 was the original x value. The y value stayed 9. The y value stayed 9. But now the y value is 2. Reason being, this told me to move them all right 5. The x value was negative 2. I added 5 to it. Now it's 3. So you can see in this chart, we're adjusting the x's because it's left-right movement. Well, there's a way that we show all of that through what's called mapping notation, which is what you see down here. And mapping notation is, to give you the analogy of why they probably call it mapping notation, it's the analogy of me handing you a paper map and saying, follow this set of directions to get from point A to point B. If you do, you will successfully get there. Well, mapping notation kind of goes with graphs. I give you a set of instructions to turn a set of ordered pairs from your base function into your new transformed function. So for example, in this example, notice what happened is we moved all the y values up 2. Well, because it was just a vertical translation, nothing happened to the x values, but the y values were increased by 2. That's why I would put a +2, so I would take all my original points and add 2 to the y values. In this one, this is the one we moved right 5. Well, to go right 5, you'd want to take all your x values and add 5 to whatever they currently were. Notice the y values, though, you're just going straight across, which means they wouldn't change. Now, they could both change. We'll look at a couple of examples here that have both transformations, but those two charts, the first one had just a vertical translation, and this one had just a horizontal translation. Look at these couple of graphs. I want to write out a mapping that would tell me how I would get the points on my base function g of x and turn them into my new function f of x. This is how I would translate it. So it says take the points x, y, don't put an equal sign here, put an arrow, map them to this new set of points. Well, you tell me what we would want to do. We would want to go right 7 and up 4. Right 7 means take all the x values and add 7 to them. That would move them all right 7. I want all the y values to move up 4. Take all my y values and add 4 to what they used to be. All right, here, I want to make a new set of ordered pairs, x, y, on my new graph, h of x, which will be created by taking function g and moving left 2. So take all your x values and go left 2. Take all your y values and go down 3. That is called mapping notation. Now, we will add other things to it. So when there's stretches and reflections, it'll force us to put other numbers in certain places, and we'll figure out where that is as those two sections unfold a little bit later. All right, so looking at, the last thing I want you to be able to do is look at a graph such as this blue one, and I want you to be able to write a new function, g of x, and tell me how the blue function became the red function. Now, if I look at this, so for example, g of x equals, well, for this blue function to arrive down here, I would have to take this point and go 4 to the left and down 5. So think about that. 4 left and down 5. That's the only changes that have been made. Now the red one looks bigger, it's just because you can see more of it. It's the same stretch factor, over 1 up 1, over 1 up 1. So this blue one or the red one, they're the same width in terms of their opening. All I have to do then is say, okay, g of x was created by taking function f, so generically function f, and I moved that function 4 to the left. I need to put a +4 inside the function, and I moved it down 5. Now in this example, I specifically know I was talking about the function x squared. So I could, rather than go with the generic version of it, which is just saying function f, whatever it is, doesn't matter, and use the specific version of it and say, well, because I know function f is x squared, I could go x plus 4 squared minus 5. Now what I find is some students don't quite grasp the difference between these two, and they kind of intermingle them when they'll put f at x plus 4 squared. Okay, that doesn't make sense. That would mean you want to put x plus 4 squared in where the x is, and that's not what we want to do. So this is the general version of it, and this is specific to the type of function. Both are right. Just don't mix and kind of put half of this one into with this one, or else then it's not right. Now let's write a mapping. So if I was to write a mapping, and I want the mapping to get the blue graph turned into the red graph. So I would take all the ordered pairs on the blue graph, f, and I would move them left 4, so take all the x values and subtract 4, and then I would take all the y values and move them down 5. So if I did that to every ordered pair on there, it would turn into an ordered pair on the new graph. That's called a transformation of f of x. And specifically, I did 2 translations, horizontal and vertical. I got another one here we'll just look at. So if I looked at this graph and I wanted to identify a function, so how did I create g of x? I created g of x by taking function f and moving. If you could look at this, they're the exact same shape. So I haven't stretched it or flipped it over or anything like that. All I've done is move it left and right and up or down. Well, this specifically, let's use a as our kind of our point. A went, I'm at -5, it went 4 right, and it would have moved down 9. It was at +2, now it's down at -7. That's a difference of 9 below it. So it moved 9 down. So now you just put numbers in your notation properly. So it would be f at x. So I want to go right 4. So that would be subtract 4. I want to go down 9. That would be subtract 9. Write a mapping. So a mapping that would get that blue graph down there, follow these instructions. Take all the x values on the top graph and add 4 to them. And then take all the y values on that top graph and subtract 9 from them, and you will generate these new points down here. If you ever doubt yourself, pick a point. Let's pick D. So right now, D is at the ordered pair 1, 3. Well, D down here is at 5, -6. Well, let me see if my rule would work. If I took 1 and I add 4, that works. If I took 3 and I take away 9, I will get that point. So it works. Okay, so that's how you identify function notation or mappings to get one function on a graph to turn into a new function on that same graph. All right, I have a quick chart that will just summarize everything we've done, and then I'll let you get to work on practicing some of this stuff on translations. So I've got this little chart that says identify the translation. They're just talking here to say, is it vertical, is it horizontal, or is it both? And then over here you specifically write out what the function notation would be and what would the mapping notation be. So let's start with this one. This one, if I have just this f at x plus 7, you can see here it's going to take the x values and move them left 7. That is a horizontal translation. I'll just put h. F at x minus 3, that's another horizontal translation. And what it will do is take all the ordered pairs on your function and move them right 3. It will not have any effect on the y values. This one is a vertical translation. It will take all your ordered pairs and it'll leave the x values as they are, but it will take all the y values and move them down 6. This one, I prefer to write it as y equals, so it's going to become f at x plus 4. Move your plus 9 over to get minus 9. So that is going to be both horizontal and vertical. It will move the x's left 4, and the y values will get dropped down 9. Okay, I have a few more with both combinations. So this one, my function, it goes right 4. Right 4 is found by putting an x minus 4 inside the function, and then down 6 would subtract 6 there. Y equals f, so now I'm going left 2. In function notation, that's f at x plus 2, and the y values are going up 3. That would be that. This would be both vertical and horizontal. This one now is just generic, doesn't have numbers, so it tells you it's both. And now this tells me that I would take the x value and move right h units. So I would add h to all the x's, and all the y values would get moved up k. And that is what are referred to as translations. All right, so that's the first type of transformation we're going to study. To follow in the next video will be reflections, and we'll probably do reflections and stretches together in the next video. It'll be a little bit longer, but we'll do those translations or transformations next. Okay, so there will be some practice for you to try in your book. As always, if you have any questions, concerns, reach out via Teams, email, ask questions in class. Best of luck. Thank you for watching.